This presentation will be on shift registers. Recall that a flip-flop holds a single bit of information at 1 or a 0, and that a set of flip-flops make up a register. It will hold what we call a word. So we're showing here an 8-bit word, or an 8-bit register holding an 8-bit word. A shift register adds another operation to the job of the register. So the job of the register is to hold, and the job of the shift register is to hold and also to be able to shift, to move all the bits in one direction or the other. So here we've shown a shift to the right. So in this example, we are showing a 6-bit shift register that shifts to the left. So we have some initial value that the shift register is holding, and then each bit is shifted 1 over to the left. There's some bit that is going out, and we've labeled that as the serial out, and there's some new bit that's coming in that we call the serial in, so that red one at the top is what's waiting to come in. And then in the second row we see after a single shift that it has gotten in the rightmost position, and then it shifts over 1 to the left and another 1 to the left as we progress down. Shown here is a 4-bit parallel loading register. And I'd like to focus on that part of the circuit that is in the red box. That is a 2-to-1 mux. And we know what a 2-to-1 mux does. A mux chooses from a number of sources, picks one and makes it the destination or the output. And so it has a 1-bit selector, and that is the L. So the L is one of the ands connects to the L, and the other connects to the knotted L, the inverted L. And so that's the two addresses. And then the other inputs to the ands are the possible sources of data, and one of them is the switch D, and the other one connects down to Q, the output of the latch beneath. And then the output of the mux is fed into the D, the data of the latch. So the latch has an input, which is the output of the mux. So we're picking one of 2 possible data sources to come into the latch, and then the output of the latch is one of the inputs. So if that is the selected input by the mux, then the data is just sort of a feedback loop. The output, the Q, is read back into the D. And then if you're choosing the other source, it is the switch coming in from the switch, and that's the sort of parallel loading part of the register that you can load from these switches, and you do that in parallel. You do them all at once. Okay, the other part of this circuit is the T switch, and that is connected to what we'll call the clock input of the latch, and that's got to go through an edge. So we will get data, we will write data to the latch when we go through a clock edge. L will determine, are we getting that data from ourselves, almost sort of a feedback hold, or are we getting it from the switch? And then we're going to change the circuit to change this weird kind of feedback hold into a shift. We'll think about that next. So the data input of the latch, the D, comes from 2 possible choices. One of them is the output of the same flip-flop, the Q, and the other is the data switch above, the switch labeled D. We make a choice between 2 possible sources using a 2-to-1 mux, and we do it by having an address or a select input, and that is the L. The L is determining the source, and the T is determining when. So when the load switch is high, we are selecting the data switches to be the data input. And then we're going to go through a positive edge of the clock. So the clock's going to go sort of back and forth, and when we go from low to high, that's the positive edge. Then we will write the data that is at D into the latch, and that data in that instance is coming from the switches. So that's the sort of parallel loading aspect of this parallel loading register. The other situation is when the load input is low, then we are choosing the flip-flop's output to be the data input also of the flip-flop. This is a type of feedback. And so again, we have to go through a positive edge on the T input. So we'll make T go back and forth, go through a full cycle. And then when it is going from low to high, that will be the positive edge. And then we will take the data that is presented to the latch into the latch. And in this case, we are just doing the latch already itself. It holds things. It's a latch. It's a flip-flop. But this is sort of a higher level of holding in this case. We can adapt the previous parallel loading register to become a parallel loading shift register by making one relatively small adjustment. Instead of having one of the two possible inputs for a flip-flop come from the output of the same flip-flop, we can change that wire and have it come from an adjacent flip-flop, a neighbor. And then when we are using that input, not from the switches, but from the flip-flops themselves, when the load input is low, then we are getting a given latch, a given flip-flop is getting its input from its neighbor, and therefore it is shifting. So you will be changing the wire indicated and the corresponding wires for the other flip-flops. If one shifts, say, from the right to the left, then we have to figure out what the input for the rightmost flip-flop is, so that that 1 in the 1's place is moved over to the 2's place, and the 0 in the 2's place is moved over to the 4's place. But what's coming into the 1's place? What is the new data input? So that could be, there could be some kind of data input. It might maybe a switch or data coming from some other place. It might be that you always make it a 1 or you always make it a 0, or you might take the output that's leaving on the other end and feed it back around and form what's called a ring. So why are we talking about shift registers? What are they good for? How are they used? They're used in modems, multiplication, adding floating point numbers, and cyclic redundancy check. CRC. CRC is not so much a use of a shift register as an error detection scheme that you can add when you're already using the shift register in the modem case. A modem is a modulator-demodulator. It takes a signal from a computer and places it on a transmission line, or the reverse process takes the signal off of a transmission line and brings it into a computer. When the transmitting modem modulates a signal, it takes a signal, a digital signal from a computer, and it creates a pseudo-analog signal that is more appropriate for sending it down a transmission line. The receiving modem is said to demodulate the signal. It's going to take that pseudo-analog signal that was on the transmission line and convert it back into a digital form. Our focus here is on the shift register. And the job of the shift register isn't so much of converting digital data into pseudo-analog data as it is converting parallel data to serial data, and the reverse, converting serial data into parallel data. This is another thing that a modem has to do. So inside, say, a processor, data moves around as words in parallel. And then when we are going to send the information out to some longer distance on some kind of transmission line, we're going to have to convert the data from a parallel form to a serial form to be sent over the wire. And then as we are receiving the information, we're going to have to bring the information in serial, 1 bit at a time, and then convert it into a parallel form. If we have a parallel loading shift register, then the data can come into that shift register in parallel, say we're inside the processor, bring it into the shift register, and then we can start the shifting process. And the shifting process, 1 bit at a time, will leave the shift register and then can be placed on the serial connection 1 bit at a time. To get the data off of the transmission line where it is serial and then into the processor where it is in parallel, you would use a serial loading shift register. So the bits would come in 1 at a time. You would be shifting the data in, and then when you have the full word of data, something could come along and read it, and so the data would move out in parallel. Let's look at this modem simulation in multisim. So we have to start off with a parallel in serial out shift register. So that is the sender, and then we will have a serial in parallel out, and that will be the receiver. So the parallel in is going to receive its data from the data switches A, B, C, D, E, F, G, H, 8 data switches. S is going to be determined whether we are shifting or loading. The little tilde in front of LD means it's loading when that input is low. And the T is a clock, and so we must go through a clock's edge each time to get an action. And then these two shift registers are sharing a clock. They're synchronized. And so as the data comes across this transmission line from QH into A and B, then that data is going to be read into the receiver shift register in serial, and then we will have the data that we fed in out. And this is to imagine this to be some long distance, this transmission line. So it'll come in parallel, it will travel across this line in serial, and then it will come back out in parallel. The pattern we're going to see is going to be low, low, high, high, low, low, high, high. So a pattern of 2 lows, 2 highs, 2 lows, 2 highs. So let's start. So turn the simulation on, and we are going to hit S. So we are loading. S low is for load, and we're going to go back and forth with T to make sure we go through a clock cycle. Then we're going to switch S back to high. So now we are in the shifting mode, and we're going to go through clock cycles. We're going to go through 8 clock cycles because we're working with 8-bit words. So 1 clock cycle, 2 clock cycles, 3 clock cycles, 4 clock cycles, 5 clock cycles, 6 clock cycles, 7 clock cycles, 8 clock cycles. And here we have the word in the receiving shift register ready to be taken out in parallel. So again, the parallel in serial out prepares the data that was in parallel to be sent along a serial transmission line. And then the serial in parallel out takes the data off the transmission line and prepares it to be once again in the parallel form, ready for, say, a processor. Let's turn that off. A cyclic redundancy check, or CRC, is done in conjunction with a transmission. So you already have the shift register that's in the modem, both in the sender and in the receiver, but you add some additional functionality to it to do an error correction scheme. So the sender will do some calculation based on the data being transmitted, and the receiver will do basically the same calculation. And if they agree on the answer, then presumably no error occurred in the transmission, or at least it's less likely that some error occurred in the transmission. Now the receiver doesn't quite do exactly the same calculation because the sender's data, the CRC, so the sender sends the data plus the CRC answer, and then the calculation done by the receiver is done on the sender's data and the CRC as a total, and then the receiver should get an answer of 0. And this is just electronically easier to test if all the bits are 0. Just imagine a great big OR gate, and if anything's not a 0, you're going to get a 1 out of it. Basically any sort of mathematical operation or logical electronic operation performed on the data that you're transmitting can be used to serve as a check. Another common error detection scheme is called a checksum, where you are adding data. So you break it up into a certain word size and add those word units. You don't want the calculation to be time consuming, and you want it to detect as many types of errors as possible. It's possible to think of CRC as a sort of a weird kind of a division as opposed to summing. And then basically it's maybe the remainder of this division that is the check, but it's not ordinary division. But it's, instead of doing something complicated like division, we just do something that's division-like, but that is easy electronically. So CRC is a shift register plus some excluded ORs. So we've already had a shift register because we are at the level of transmission and we were shifting anyway. And so now we add some excluded ORs to do this CRC calculation, this error detection scheme. And it just adds excluded ORs in certain strategic positions to try and find the most common errors. Now what we're looking at here is a very simple CRC. I've got a 4-bit shift register. I've labeled the positions A, B, C, D to be able to talk about them easily. And then I've inserted 2 excluded ORs between A and B, and then between D and the new data that's coming in. The second input to those excluded ORs is the bit that is in position A in the previous step and getting ready to sort of leave, to be shifted out. So the first 4 steps are boring and the data just sort of shifts in because I started with all the zeros. And so the data just shifts in 4 steps, and I'm a little bit impatient. So that from row 1 to row 2 is really 4 steps, but they were all sort of just boring shifts. Nothing was going on interesting with the excluded ORs. Okay, now let's go from row 2 to row 3 and see what's happening. So in position C, the red, these are the simple ones to talk about. The red that was in position C is simply shifted to position B. So when going from row 2 to row 3, the 0 in position C shifts to position B. Very simple shift. Same thing again, from row 2 to row 3, the 0 in position D is simply shifted into position C in the 3rd row. Now the interesting stuff, the excluded ORs. So in row 2, I have a 1 that's in position A and getting ready to leave, but it is the input to some excluded ORs before it leaves. And so the A in row 2, the A that's about ready to be shifted out, and the B that is ready to be shifted in, they get excluded OR'd to become the A in row 3. And so 1 excluded OR with 1 gives me a 0. So that's where the 0 in position A in the 3rd row comes from. The other excluded OR is at the other end. And so I have, again, in row 2, I have in position A 1 getting ready to be shifted out, but before it's shifted out, it comes back around and is one of the inputs to the excluded OR. And the other input to that excluded OR is this new bit that is being shifted in. And so that was a 1 in position A and a 0 that's on its way in. And 1 excluded OR with a 0 gives me the 1 that you see in position D in row 3. And then you just repeat and repeat and repeat. And so the procedure just continues the shifting and the excluded ORing until all the data has been shifted in. So let's look at, again, going from row 2 to row 3. In row 2, in position C, we have a 0, and that simply shifts over, as the red arrow indicates, into position B in row 3. And in position D in row 2, that 1 just shifts over to position C in row 3, indicated again by the red arrow. The 1 that's in position A in row 2 and the 0 that's in position B, they are excluded OR'd and give us the 1 that is in position A in row 3. And the 1, again, that's in position A is excluded OR with the 0, the first, that 0 on the left then is coming in. And again, the 1 and excluded OR with 0 give us that 1 in position D in row 3. Next, we're going to turn our attention over to another use of the shift register, which is in multiplication. So let's remind you of decimal, and then we will look at the binary version. So one way to achieve 1, 2, 3 times 3, 2, 1 is to take the first number 1, 2, 3 and multiply it by the 1 in the ones place of the second number. And so that's that green 1, 2, 3 displayed. Next, we will multiply our first number 1, 2, 3 by the second number's 2 and is in the tens place. And so that's the blue 2, 4, 6. Note that it is shifted over compared to the 1, 2, 3. And then we're going to multiply the 1, 2, 3 by the 3 in the hundredths place. And 1, 2, 3 times 3 is 3, 6, 9. And this one is shifted over twice. And then we add all those various numbers and get our final answer. It's the same in binary, only simpler, because the only digits you are multiplying by are 1 or 0. And when you multiply by 1, you recover the same number. And when you multiply by 0, you get nothing, you get 0. So I'm going to multiply 1001 by 1011. And so I start by multiplying 1001 times that 1 in the ones place. And I see that result there in the row I've labeled A. Now I'm going to multiply 1001 by that 1 that's in the twos place, and that gives me my shifted 1001 that I've shown in row B. Next, I multiply 1001 by the 0 in the fours place. Multiplying by 0 gives me 0. So in row C, I just have a bunch of zeros. And then finally, 1001 times the 1 in the eighths place gives me that answer, that 1001 in row D that has been shifted 3 times. So we are shifting and adding. Multiplication in binary is just a combination of shifting and adding.